talking about sending humans to Mars has become almost casual. Space agencies announce plans, private companies publish timelines, and public discussions often frame Mars as the obvious next destination after the Moon. The idea has become familiar enough that it no longer feels extraordinary. But familiarity hides the true scale of the challenge. When you move past headlines and slogans and actually examine the physics, biology, and engineering involved, it becomes clear that a human mission to Mars is not merely difficult. It may be the most extreme undertaking in human history. At the heart of the problem lies distance. The Moon, Earth's closest celestial neighbor, orbits at an average distance of about 384,000 kilometers. Apollo astronauts reached it in roughly 3 days. Even at that distance, the missions were risky, but Earth was never truly far away. If something went catastrophically wrong, the crew could return relatively quickly, and mission control could provide real-time assistance. Mars exists on a completely different scale. Even at its closest possible alignment, Mars is about 55 million kilometers from Earth. On average, the distance is closer to 245 million kilometers, and at its farthest, more than 400 million kilometers separate the two planets. These distances fundamentally change what a space mission means. They turn spaceflight from an expedition into an extended exile. Because of the enormous energy required, spacecraft cannot travel directly to Mars in a straight line. Doing so would require impractical, almost unimaginable amounts of fuel. Instead, engineers rely on Hohmann transfer orbits, carefully calculated, fuel-efficient paths that allow gravity and orbital motion to do most of the work. The trade-off for efficiency is time. A one-way journey to Mars typically takes about 7 months. Once you account for the need to wait on Mars for the planets to realign, a round-trip mission lasts at least 2.5 years and often closer to 3. This is not a short adventure. It is a multi-year commitment with no possibility of early return. Once astronauts leave Earth orbit, they are committed, regardless of what happens next. Even the timing of Mars missions is dictated by celestial mechanics. Earth and Mars align favorably only once every 26 months. Missing a launch window doesn't mean waiting a few weeks. It means waiting more than 2 years. This creates immense pressure on mission planning. Technology, funding, crew readiness, and political will must all align perfectly at a specific moment in time. A single delay can unravel years of preparation. Distance also destroys the concept of real-time communication. Signals between Earth and Mars take anywhere from 3 to 22 minutes to travel one way. In practical terms, this means astronauts cannot rely on immediate guidance from mission control. In an emergency, they must diagnose problems, make decisions, and act entirely on their own. Advice from Earth may arrive long after the critical moment has passed. This level of autonomy is unprecedented in human spaceflight. During Apollo missions and on the International Space Station, ground control played a constant role in troubleshooting and decision-making. On Mars, that safety net simply doesn't exist. The crew must be capable of handling every crisis alone, making them the most isolated humans who have ever lived. That isolation is not only operational, it is deeply psychological. Astronauts on the International Space Station can look out the window and see Earth filling their view, vibrant and close. They can speak with family members almost instantly. On a Mars mission, Earth slowly fades into a distant point of light, eventually disappearing entirely. Everything familiar, home, family, culture, history, exists only as a memory. The spacecraft itself must function as a closed, self-sustaining ecosystem. Every resource must be recycled. Oxygen must be regenerated from carbon dioxide. Water must be recovered from humidity, waste, and even urine. Food supplies must last for years. There are no resupply missions and no spare parts arriving later. If something breaks and no replacement exists, the crew must improvise or accept failure. This is where the rocket equation becomes brutally unforgiving. Every additional kilogram of supplies increases fuel requirements exponentially. Engineers must make painful trade-offs between redundancy and weight, between comfort and survival, between scientific ambition and safety. There is no room for excess, yet failure is not an option. Radiation adds another invisible threat. Beyond Earth's magnetic field, astronauts are exposed to solar particle events and galactic cosmic rays, high-energy particles capable of penetrating spacecraft walls and damaging DNA. Over the course of a Mars mission, astronauts could receive radiation doses equivalent to centuries of natural background exposure on Earth. This significantly increases lifetime cancer risk and may exceed current career limits for astronauts. Weightlessness further complicates survival. In microgravity, muscles weaken rapidly, bones lose density, and the cardiovascular system adapts in ways that may be dangerous when astronauts arrive on Mars. Vision problems, immune system changes, and fluid shifts in the body are already observed on 6-month missions aboard the space station. A Mars mission would last several times longer. Mars itself offers only partial relief. Its gravity is about 38% of Earth's, enough to feel weight, but far less than what the human body evolved to handle. We have no direct data on how long-term exposure to partial gravity affects bones, muscles, or organs. This uncertainty represents one of the greatest biological unknowns of interplanetary travel. One proposed solution is artificial gravity. By rotating parts of a spacecraft, centrifugal force can simulate gravity, helping to preserve muscle, bone, and cardiovascular health during transit. While promising, this approach introduces major engineering complexity, increases spacecraft mass, and raises costs dramatically. Still, it may prove essential for protecting crew health. After months of travel and years of preparation, the mission reaches one of its most dangerous phases: landing. Mars has an atmosphere that is thick enough to cause extreme heating during entry but too thin to provide sufficient drag for safe deceleration. Spacecraft must rely on a precise sequence of heat shields, parachutes, and rocket engines during a brief window known as the 7 minutes of terror. Once this process begins, there is no human control. Everything must work perfectly. None of this means that sending humans to Mars is forbidden by physics. The equation's close. The trajectories work. The challenge lies not in possibility, but in reliability. A Mars mission demands systems that must function flawlessly for years, crews capable of surviving extreme isolation, and solutions to biological problems we are only beginning to understand. Going to Mars is not simply a longer version of going to the Moon. It is a fundamentally different kind of endeavor, one that pushes against the limits of physics, engineering, biology, and human psychology all at once. If humanity succeeds, it will not just be a technological achievement, but a profound statement about our ability to survive beyond the world that made us.